Getting the game loop right. Let's say you're writing a game from scratch. One of the first things you want to do is create a game loop, which is basically an infinite loop which deals with the simulation and drawing of your game. The most basic loop will call the update function and the draw function on every single iteration. With that in mind, let's see how the loop behaves when there is a single character on the screen moving at 1 frame per second. As you can see, if we assume that the velocity of this character is 300 pixels per iteration, it will consistently move 300 pixels per second. Now let's see what happens when the number of frames per second is different. As you can see, the speed of the game is twice as fast. This gets even worse if the number of frames per second increases further. This is of course not desirable, as we'd like the game logic to be consistent and run at the same speed regardless of the hardware of the user. One of the ways we can achieve that is by calculating the time elapsed between each frame, commonly called the delta time. Doing so is quite easy. All you need to do is use your system clock or the clock provided by your favorite library in order to take the time points at each single frame and then subtract the previous frame's time point from the current one in order to get a difference. Then we can pass that delta time to the update function so that any calculation can be multiplied and scaled by that time difference, ensuring consistent game speed regardless of the user's hardware. Let's see how that looks with our character. As you can see, rather than moving the character by a fixed amount of 300 pixels per iteration, we're actually multiplying the character's velocity by the current delta time, which is going to be 1 in this example. Let's now see what happens if we run the game on a machine which is twice as fast. Despite requiring double the amount of frames for our character to reach the target, the game speed is still consistent. As you can see, the multiplier for the velocity is now 0.5, which means the character will move half the distance on each frame, which makes the game behave the same, as now the number of frames per second is twice of what it was before. So, what's the problem with this approach? Well, the issue is that even though the game speed is consistent, the number of pixels that the character moves each frame varies from machine to machine. And this can affect things like physics, collision detection, and other parts of the game logic. As an example, if there is an obstacle in the way of the player and the frame rate is low enough, then the offset of the player movement between two frames might be so large that the collision between the player and the obstacle is completely missed. But this is not the only issue. Other than the precision being too low, and thus missing collisions for example, it can also be too high, leading to simulation instability, especially if using floating point numbers and the numbers get really small. Another issue that is not always considered is the fact that your simulation is now indeterministic. While this might not be a problem for some games, if you want, for example, to implement a replay system, or if you want your inputs to always lead to the same outcome, regardless of the speed of the machine, indeterminism will make these things almost impossible to achieve. So what can we do? Is there any way we can get consistent game speed, determinism, and a predictable experience on any hardware? The answer is yes. So let's go back to the drawing board and see how this can actually work. Since we want our simulation to be predictable and deterministic, let's first choose a fixed frequency for our updates, which is commonly called a tick rate. As an example, our tick rate here will be 1 update per second. As before, we'll keep track of the time elapsed between two frames. In this case, as you can see on the graphic, T0 will be the time point of the first frame, and T1 will be the time point of the second frame. Now let's assume that the time elapsed between T0 and T1 happens to be 4 seconds. So according to our tick rate, we are going to have 4 updates in total, which are going to be represented by the red lines here on the screen. This scenario shows the case where the time elapsed between two frames is quite high and way higher than the expected tick rate, which is 1 updates per second. This can happen if the hardware is quite slow or if there is any lag spike happening at the moment. Let's now take a look at another scenario. In this case, the time elapsed between frames will be much shorter, and it would actually be lower than our tick rate. On the screen, you now see 5 frames, and the time between them is 0.5 seconds. So when do we actually execute the updates? Well, we know we want 1 update per second, so we know we can execute them at T2 and T4 respectively. If we now step back and look at the two cases in comparison, you'll see that the time elapsed between frames doesn't really matter, and we always get our desired tick rate, which is again 1 update per second. This means that independently of the hardware our game will be executed on, we'll get a consistent game experience and everything will be fully deterministic. Let's now take a look at what the code for this would look like. Of course, we'll start with our game loop, and then, like before, we'll keep track of the delta time between frames. We will also now accumulate all the elapsed time since the last update. And now this is where it gets interesting. We'll define tslice as the time we want to be elapsed between updates, and we will loop while our accumulator is greater than the slice. Inside the loop, we will call update with a fixed step for our simulation, which can be tweaked depending on whether we want our simulation to be less or more precise. And on each iteration, we will also subtract the slice from the accumulator. Remember that the slice is a time that we choose, it depends on our tick rate, and is basically the time we want to be elapsed between updates in our simulation. Now, all that's left to do is to render our game. We can do that on every iteration of the loop, and that's pretty much it. What I like about this game loop is that, as I mentioned before, it is always going to be consistent in terms of game speed independently of the hardware of the end user, and also it is fully deterministic, as the step that we pass to update is a fixed value which guarantees that the same inputs given at the same time will always result in the same final behavior, assuming there are no other sources of indeterminism in your game. If you properly choose a slice and a step for your game, you will never have issues like your character missing a collision or the time step being too small or too large for the precision to behave correctly in physics simulations and things like that, which eliminates an annoying class of bugs you might have had before. There's also several ways you could improve this loop, and I'm actually going to put some links down in the description that give you some ideas. But for example, rather than drawing the current state at each frame, you could interpolate between the state at the last frame and the new one. That will make the drawing look smoother even if the rate of updates is quite low. Another possible improvement would be to limit the maximum amount of updates that can be done in a single cycle. So on very slow hardware, you would prevent the game from hanging for a very long time, with the compromise of the game speed being affected. That's all I have for you today. This was a new experiment for me. I've never done a video like this before, where I'm using, graphics to explain these concepts and trying to dive deep into the code step by step. So please let me know if you enjoyed it and if you want to see more of this. It's definitely time consuming, but I had fun making it. So thank you so much. Let me know what you think in the comments, and good luck on your game development journey.